Welcome back to Gamers, another Jogamin video. So last video we derived the equation of a circle, full area of a circle. Now, the real question now is, how do you derive the area of a sector? Which, I mean, if I'm being honest, I haven't done that yet either. I'll explain a way to do it. I'm not gonna derive the equation. Alright. Now this kind of looks like the freaking zodiac killer symbol, but so sectors are portions of the circle made by two radii. Or that's at least what I want to think it is. So something, this is not gonna be ridiculous. Yeah, okay, so let's make a line. Don't know how this is accurate, but it's something like that. That's not good. Can I just copy this? Just rotate it 90 degrees. Oh crap. Alright, that's fine. Can't even like select the object. It's so trash. Anyways, let's see, this is now, I've been doing a little bit of tinkering with decimals and stuff, and I came to realize you're probably not going to derive 1/2 theta r squared as is easy calculus, and if you do, it's probably a lot more, probably more than I can do right now, or too lazy to use. But let's just start with a simple sector. Right? Let's say we got a sector, let's say this is from two sides. We're not going to consider these sides, alright? That's going to just use symmetry, like that's the main idea about sectors. If you have a sector that is like, that is in different quadrants, you know, like this, or maybe even this, just use symmetry. Like, I don't know what to say, like, just use symmetry on these, on getting the area, because this technically, let's say this is symmetrical, like this angle right here is 90 degrees bigger. If this was exactly the same, like, this area would be equal to this area and you get 0. But with symmetry, you just get, if you knew this angle is the same as this angle, you just multiply by 2 the whole thing this area, right? And if it wasn't the same, like let's say this is like 60 degrees and this is like 30, I don't even know why I added up this rate, I don't even think that's why. Whatever angle this is, this has to be less than like 180 or something. Yeah, let's say, I don't even care. Just say random angle, right? You know what you'd rather do, since getting integral of these literal pieces will get you a negative number because this area is greater than this one, right? What you'd rather do is get the 60 degree angle right here, get the area of, how should I explain this? You just get the, hold on. Yeah, so for this scenario, you would just get the integral of this line and the circle, since the circle's on top of the, let's say this function's the circle minus the function of the line, g of x, from wherever this x is to 0. And then you plus the integral from the 30 degree angle, wherever this slope is, times, I mean, the same thing, plus this thing, but this line is different, right? That's what you would do for that. But it's a lot more nuanced than what I just explained. And if your sector looks something like from here to here, like this whole area, maybe even like you wanted this entire area, you just get this area right here, and you get this area right here. Well, positive, so you're probably getting absolute value of this, right? And then for here to here, due to symmetry, you can just get the area of 1/4 circle, multiply that by 2, and add it on to this part. And, or you know what, if you want to make things more cooler, whatever this angle is, the theta right here, you'd make a line like just like that with the same theta here, and add it to this and this. You know, that's what you probably do. But we're not focusing on that. We're focusing on if it's between, anywhere between here and here. If it's a point, let's say you have a point from here to here, like let's say that's R1 and R2, right? To get the area of this sector, it's actually a little bit different from getting from here, from this sector versus this sector, just a little bit. Now, what I'm going to tell you, maybe I'll do this all in one, maybe 3 videos, but I'll show you first how to get the area from this sector, this whole sector, between two quadrants, and then I'll tell you how to get the sector of two points in the same quadrant, and then I'll tell you if that smaller one is in the same quadrant, whatever. If this smaller one is inside a bigger one, how would you use this smaller one to get the area of the bigger one due to symmetry, like I was talking about earlier. So yeah, that'll probably gonna be 3 videos. I mean, in total 3 videos, exactly. So yeah, let's get started with it. So let's say we got just at least something. A sector between 2 quadrants, and what I mean by that is that the first line is within 90 degrees, and the second line is over 90 degrees in rotation. So anything past this line, this 90 degree rotation line, is going to be considered second quadrant, sector line, whatever, or something like that. And when I was trying to derive the equation for a sector, which is this, right, I needed to find theta, but I mean, to prove my method I showed last video without using theta, or at least I thought so, I need to check my answer with the real equation that I know of. And I spent a lot of time actually trying to find this theta using this example, and it was just me doing careless mistakes. So here's what I thought. Let's first find this theta right here. So this angle theta right here, and this angle made by this radius right here, and this angle right here, let's call this theta 3, theta 1, 2, and 3. And as we can see, it makes a full 180 degree rotation, so therefore theta 1 plus 2, who writing this summation for me? Theta I, where I equals 1, to 3 equals pi. I'm not writing theta 1 plus 2. This is fast, alright? This is fine. So theta I from 3 to some is equal to pi. Now, here's the thing. How do you find the angle of these freaking lines, so to speak? So, first thing you should do is imagine these lines as triangles, of course, because you're trying to find the angles, so you should relate them to the trig and the triangles. So we got this line, which is like so okay, we got that line and this line. Right. So first off, let's call this position x1 and this radius r1 and this radius r2 and x2, right? We're trying to find the theta angle of this for now. What would be the angle of this line? Well, in order to find that line, the angle, okay, so we know from what's given already, we know this is x1 and that's r1. So r1 over x1 equals cosine theta. Right? Alright, so I'm back. Anyways, so I don't know why I'm really finding the angle. It doesn't matter for the integral, but it's just to check your work. I don't even know why I'm doing this, but just showing you. So theta let's call this 3 equals r cos x1 over r1. And you would think, you'd probably think that, wait, hold on. So here's where the discovery happens, this is why it took so long. So when I was trying to find the angle here, let's call this angle 2. So since it's on the second quadrant, the x value of this is actually negative, right? So I did r cos, and then it was a negative value of x2. Let's say x2 on this side would be right here. This side would be then the negative x2. So since I used that negative x2 over r, I actually got the wrong angle. And the reason behind that is because of how r cosine works. And that once the angle has passed this 90-degree angle, r cosine doesn't reset, and then when you have it doesn't, and then when you go over here and get the r cosine here, you're not doing that. It actually continues off of the angle right here. So basically r cosine of negative x whatever is actually getting this whole angle. So basically the sector angle plus this angle, which would honestly just mean that all I had to do was get this minus this angle to get the sector angle, but I didn't see it like that. And so basically I got the calculation wrong for adding up the angles to find the sector angle, but ignoring that is where I got that wrong. This is why I'm talking about symmetry. And to really get this angle right here, what you do is r cosine negative, if the value is negative. So yeah, basically to get the actual angle you want, you would have to subtract r cosine negative x2 over r by pi. Which, I mean, you probably didn't think it'd be pi, and I honestly guessed it was fine and it worked. It doesn't work for any other arc thing. If you try with arctangent, it's not going to work with pi, and I don't know what angle you have to subtract it with. But I do know a method that works for both arctan and arccosine to get the angle you want, and that's called removing a negative. And so the real angle I actually wanted was just x2 over r. Yeah, I mean you could just do pi minus, but that doesn't work always. I'm not trying to remember equations here, so I just get the just remove the negative, and this is the actual angle you want. And so I'm basically saying, yeah, and then you solve for theta and you get the theta that you want here to prove that your integral actually gets the value you want. But that doesn't matter just now. It doesn't matter now, right now. What matters is the integral that gets you the equation of the area between here and here. Now, here's how it's set up. So let's see what we have to do first. So notice that I drew a line at x1. The thing about that is if I want the area from here to here, which is 0, basically there's a problem. So let's say there wasn't this line here, we'll move the line. If I got from 0 to x1 the integral from x1 to 0 of this circle equations f of x, I would not be getting this sector. Matter of fact, if you thought just getting the integral from x2 to x1 would get you the area of the sector, you'd be wrong, because there's this extra area right here that the circle actually gets. So you cannot get this. You cannot get the area from there to there. You must do what's it called? Area in between curves, whatever. I don't know what's it called. But anyways, so the equation of this line, since it's at the origin field plus b, so therefore the equation of this line is simply just the slope of this line. And the slope of this line is well, if we said f of x is the circle, if it is this circle's is the circle the function of the semicircle, that just means that the slope of this line is f of x1 over x1 times x. That's the function of the slope. And any line. Then we just subtract it since the line is on the bottom, and it shares the mutual area between the circle and line. It shares this area, and we want to get this area. That means we have to subtract it from the actual function itself. And that's the integral from 0 to x1. Let me just write it out better somewhere else. But you know that. And then from here, this is 0 to x2 or x2 to 0, so it'd be 0 x2, and same ordeal. Just get the function minus this line, right? So in all, the area of this sector is okay. This two-parter, I guess. So f of x minus f of x1 times x plus, and this is all integral from 0 to x1 dx. Forget that. Dx plus the integral from x2 to 0 f of x minus f of x2 over x2 x dx. So yeah, I mean, technically, I think if you combine these integrals, they would be x1 to x2, and it would just be, if I factor it out, I'm not factoring actually, right? That'd be 2 times f of x, and then minus the sum of the two lines. Dx. I think this is how it could be. Let me go try that out with contest. Yeah, so of course this equation wouldn't work if, of course, that this x. Wait, I didn't write x here. Right here. If these lines actually started from the origin and ended at x1 and x2, then this equation would technically work. But since we're probably assuming that this line is actually a line, like a real line, then it's not gonna work, obviously. You get the idea. And this equation, don't worry about this equation. But here is the real. That is the real equation right here for area of the center between two quadrants, especially the ones right next to each other, first and second. So yeah, there it is. Next video, I'll show you something else that's related to this. Bye.